Continuing with magnetic effect of current, in this video we will study force experienced by a current carrying conductor in a uniform magnetic field. Whenever we subject a current carrying conductor to a magnetic field, it experiences a force. Here in this diagram you have a conductor of area of cross section A carrying a current I towards right. L is the length of the conductor and the magnetic field has been applied in the upward direction. The conductor is in the plane of the board. The direction of the force on the conductor is given by Fleming's left hand rule. According to the rule, if the forefinger points in the direction of the magnetic field, central finger in the direction of the current, then the thumb gives direction of the force. In this diagram, since the field is upward, so you should have your forefinger of the left hand in upward direction, the central finger towards right, then the thumb will point out of the board. That is, the force on this conductor will be acting out of the plane of the board. Now let's see what is the cause of the force. We know that the current through a conductor is caused by the electrons drifting in opposite direction. Whenever we have a charge carrier moving in magnetic field, the charge carrier experiences a force which is known as Lorentz magnetic force given by Q V cross B. The force on various free electrons in the conductor adds up to give us a net force on the conductor. Let's now proceed to obtain an expression for the force. For the purpose, we go back to this conductor in which we are taking N as the number density of free electrons, that is number of free electrons per unit volume. L, as said earlier, is length of the conductor, A is area of cross section of the conductor, and B is intensity of the magnetic field. Vd, as usual, denotes the drift velocity of the electrons. Since the current is towards right, the electrons will drift in the left direction, that is against the direction of the current. Force on each free electron we denoted by small f given by Q V cross B. Here Q is minus E because we are considering electron. The velocity is the drift velocity Vd. Direction is marked in the diagram Vd cross B. The total number of free electrons in the conductor is given by N, the number of free electrons per unit volume, multiplied by volume of the conductor. Now, volume is given by area of cross section multiplied by length. So total number of free electrons will be N into the volume Al. Therefore, the force on the conductor is given by capital F equal to force on each electron multiplied by the number of electrons, that is NaL multiplied by small f or minus E Vd cross B. Rearranging the terms here, let's combine N, A, E and Vd. We can rewrite the expression for force as N, E, A, Vd into L cross B. Here we have made a change. We have taken Vd, the drift velocity, as scalar, and La vector, and we have removed this negative sign because L is a vector opposite to drift velocity or along the direction of current. Since the direction of L is opposite to Vd, we can drop this negative sign. Then you know that NeVd is current I, therefore the final expression for the force is I L cross B, or the magnitude of the force is given by BIL sin theta. The direction of the force is given by Fleming's left hand rule in a special case when the current is perpendicular to the magnetic field, or length of the conductor is perpendicular to the magnetic field. In general, you can find direction of force by right hand rule applied to L cross B. The force will be perpendicular to L, force will also be perpendicular to magnetic field, as is always inherent in the property of the cross product. Now let's take a few special cases when L is parallel or anti-parallel to the magnetic field. Force is 0 because theta is 0 or 180 degree, and the force is maximum for L perpendicular to B. That is, the maximum force will be BIL sin 90 or B into I into L.